Okay. If we have problems with sound today, I'll try this other technique.
All right.
But at the moment, it sounds pretty clear to me. I don't hear any choppiness or echo or anything.
Yeah, my Wi-Fi's been being nice today, so we'll see.
Good.
Okay, so last week we had a test over factoring, and we got it back today, and I got an 85 on it.
Okay.
Which is so far the best I've done on a test. Like, I know I can do better because all the mistakes I made were dumb. Like, they were really dumb mistakes.
Okay.
But yeah, it's better than I did last time, so that's good.
Well, good.
And then we spent the majority of the period going over our test. So we didn't have any new, like, homework today or new problems.
Okay.
But he said the next thing we're going to go over is like radicals and square roots and multiplying and subtracting and adding them.
Okay.
And all that good stuff.
Okay. Do you have some problems from the next chapter that we could
I do not.
look at?
Okay.
No,
I think I can. Anything, so.
Let's look at square roots.
Okay.
Simplify that for me.
So you break it down into two. That, like, one that can work, so you have 4 and 5.
Uh-huh.
Right?
In other words, it's utilizing this principle, that the square root of any number is equal to the square root of one of its factors times the square root of another factor. And this is an integer. I can replace that with 2. So that's equal to 2 root 5. And that's how we simplify radicals. So let's do a little bit of practice on that. What's that equal to?
Well, you have to multiply them, right?
Uh-huh.
So, I don't know.
Right?
You can, yeah.
Okay. The problem is that this is not simpler than this. So root 10 would be simplified already. In other words, breaking it up into 2 radicals doesn't simplify it. The only thing that simplifies it is if you can pull out a whole number. In other words, when we had root 20, I was able to make it root 4 times root 5, and root 4 is equal to 2. So always simplify it to the point where you can pull out whole numbers, but not beyond that. Don't take one radical and turn it into 2. So let's look at this one. Simplify that for me. The trick here is to find factors of 80 where one of those factors is a perfect square. Okay? One thing that's going to be helpful is to memorize the perfect square numbers. So give them to me. If I start with 1, 4, 9, give me the rest of them. In other words, this is 1 squared, 2 squared, 3 squared. Give me up to
16,
10. Okay?
25, 36, 49, 64, right? And then, oh god, not 81.
Yep.
Oh, it is? Okay. And then 100.
Okay. That's all you need to memorize, really. Actually, it's very helpful if you have these memorized. In other words, so when we do a problem like square root of 80, we're looking for one of the factors to be one of these numbers.
Okay.
So what would the biggest one be?
I don't think think 16 goes into 80. Oh God.
It actually does, but even
does?
if you didn't, yeah, even if you didn't know that, you know that 4 does, right?
Yeah.
So let's work with 4 because it's not necessary that you get the biggest one. You will always get to the same answer. So this becomes 2 root 20. And then what does root 20 factor into again?
Is 4 and 5, so 2 root 5.
Okay, so now this becomes 4 root 5, right? Because this becomes a 2. 2 times 2 is 4. So I get to the final answer even though I didn't find the maximum factor. Had I seen that 16 is a factor of 80, I could have done it more direct and gotten immediately to this step here. But don't spend a lot of time looking for the biggest perfect square. Even if you find the smallest perfect square and start working with it, you will whittle it down until you get the final answer, if you know what I'm saying.
Yeah.
Okay, let me give you some others here.
So you would get 10, right? You could take 100 out,
Right.
which would give you 10, and then root 2.
Good.
Oh. Okay.
In other words, the same rule that applied for multiplication applies for division. Is that if I have the square root of a quotient, it's equal to the square root of the numerator divided by the square root of the denominator. So what would the square root of 9/4 be?
3 over 2, so 1 and 1/2. Yeah.
Uh-huh. All right, let me think for a moment. Tell me what this is.
Um, 10, 30?
No, that's 7 root 3.
Oh.
If
Yeah.
a root 3 equals an apple, and I have 2 apples there, and I'm adding 5 apples there, I'm going to end up with 7 apples.
Okay.
What's the product of them? Equal.
Okay. So you'd get 10 root 9, so 30?
Uh-huh. In other words, you multiply everything. You multiply that by that, and you multiply that by that, and then you take your result and multiply those two together. Remember that the root of anything times the root of the same thing is always equal to that. What's this equal to? It's what square root means.
Oh, really? So we have it.
Yeah.
Okay.
This is cube root. So if I said 16 to the 1/2, that's equal to 4. And if I said what is 8 to the 1/3 equal to?
2.
Okay.
Right?
Uh-huh. Let's see. If we're multiplying with exponent, well, let's see. You said radicals. Let's try to stick to radicals. Trying to think of radical problems. What's this equal to?
That would be 35 radical, and then you have to... Okay.
Actually,
So
that cannot be simplified. That is the final correct answer.
Okay.
And the reason is that the only factors of 35 are both prime numbers. So you know they can't go down any further. In other words, if you have a radical of a prime number, it's simplified. This is why I'm not sure if this problem is coming up for you. It's definitely coming up soon. I don't know if it's going to be in this chapter or not. And I'm just kind of pulling stuff out of the air here. So it really would work better if you can pull problems from the chapter coming up, and we'll go over them early. And I think that's helpful to you.
He didn't tell us which chapter was coming up today. I know that he just said that we're going to go over, so like square roots and then cube roots, and we're going to start multiplying them, and that there's going to be a chapter on fractions coming up.
Okay. Now let me think what that means. Square roots we've covered. Do that one.
Okay. So what goes you get 45. Could you maybe.
Yeah, the best way to do this is to divide first.
Oh, really?
Uh-huh. Because if you simplify this, you get 9 root 5, which is 3 root 5. And then you have it all over root 3. It's tough to do much with this, but let's talk about something else here. Why, that reminded me of something. Yeah, the answer is root 15. Sorry. Didn't mean to. In other words, that's root 15. No, I just got off on a tangent, wanted to talk about something else. One thing that math dictates is that we never have an irrational number in the denominator. So this is never a satisfactory answer to give. And the way we handle this is with a process called rationalizing the denominator. The way we do this is we're allowed to multiply any fraction by 1 without changing its value. So I'm going to multiply this by root 2 over root 2, turning it into root 2 over 2. This is the same exact number as that if you were to put it into your calculator, but this is mathematically acceptable because it has a rational number in the denominator. This does not. Root 2 is irrational. So every time you're working with radicals and you end up with a radical in the denominator, you have to rationalize it.
Okay.
So if I said
Okay. Problem time. So you have... So would you multiply the bottom two first?
Yeah, that's one way to do it.
Okay.
So that gives
so you
us
get,
what?
root 3 over root 10.
Okay.
And then you have to break up your root 10?
No, we just put it together, so we don't want to go back in the same direction. Now we have to, root 10 is actually as simplest as it gets. You can't simplify root 10 any. But the problem is we have this irrational number in our denominator, so we have to rationalize it.
So you multiply by root 10 over root 10?
Uh-huh.
And then you get root 30 over 10, and then you divide that, so you get root 3?
No.
No, you don't?
No, because this is root 30 over the number 10,
Yeah.
not root 30 over root 10. Whether root 30 is simplified or not, let's see if there's anything. What are factors of 30? 15 and 2.
6 and 5, 3 and 10.
5, 3 and 10, none of which are perfect squares. So of our list of perfect squares, 30 is not divisible by any of these numbers, which means it's simplified. So that's our answer, root 30 over 10. Can't reduce this any, can't simplify it anymore.
So it's just how it is? Okay.
Yeah. Let's see, let's cover a rule of exponents, because the moment you start working with radicals, well, hold on a second, let's do a couple of problems. Let's solve this equation.
Okay.
The way we would do it is to square both sides. Okay?
So you get 5 is equal to x squared plus 25.
No, remember this does not, remember how to do a plus b squared. It's x squared plus 10
Oh, yeah.
plus 25. So now we have x squared plus 10x plus 20 equals 0, and we would have to use the quadratic formula to do that. I can tell that this is going to have only complex solutions. And that's not important. What's important is how we solve equations that have radicals in them. You isolate the radical and then square both sides. So if we had something like this, let's make it like that. How do you solve this?
Okay, so you square the whole thing.
Not yet. Remember,
Not yet?
Isolate the radical and then square both sides.
So subtract 2. And then
Yeah, because notice what happens if we square both sides now. We're going to have a middle term that has a radical sign in it still. So until we isolate it, we don't want to square it. So now we get radical 7 equals x minus 2. Now we square both sides. We get 7 equals, what's that squared?
So, 1 second, I have to write out my thingy. 4x squared negative. So negative 4x squared minus 4x plus 4? Yes.
So now we have x squared minus 4x minus 3 equals 0. And that does not factor nicely either. This does give you real solutions, It just doesn't give you nice solutions that we can get by factoring. In other words, if we use the quadratic formula here, we would get x equals 4 plus or minus 16 minus 12 all over 2. So we get 4 plus or minus 2 all over 2. Why did this not, yeah, my question is, why did this not factor nicely? This should, because we get 3 or 0. No, 2 minus 1, 3 and 1, which means it should have factored into 3 plus 1 and 3, or x minus 3 and x minus 1. What the heck did I do wrong here? No, minus b is 4. 16 minus, this is plus 12. So it's 28, which is 4 root 7. In other words, when you use the quadratic formula and you come up with whole numbers, it means you could have factored it. This, on the other hand, comes out to be plus or minus, and that's going to be 2 root 7 all over 2. So this has irrational answers. I now want to split this up into 2 fractions like that. So I get 2 plus or minus root 7. Notice that that is a real answer to our problem, but it's not an integer. It's an irrational number.
Okay.
But it's not imaginary. Okay, let's see what other problems I can think of.
Is there anything different with cubed roots?
Well,
Like any rules about that?
yeah, let's talk about that. Oops, excuse me. That's equal to x to the 1/3. So what is 8 to the 2/3 equal to? When you have a number to a fractional exponent, what it means is it's 8 squared, the cube root of that. Or the cube root of 8, the answer squared. And always do the denominator first on these problems. And you'll see why. What's the cube root of 8?
Cube root of 8 is 2.
And 2 squared?
Is 4.
Right.
And
Now, if we did it the other way around, if we squared 8 first, we would get 64, and then the cube root of 64 is 4. But the problem with that is we're dealing with bigger numbers. We had to deal with the number 64. When you do the denominator first, you ensure that you deal with the smallest numbers possible. Okay, so this is what fractional exponents mean. It means the cube root of, and that answer squared.
okay. So it's like, yeah, that makes sense. I get that. So, I'm trying to think of what else he said. All the other classes got to start the new chapter today, except for ours, because we have these 2 boys that can't shut their faces.
Really?
Yeah, it's frustrating.
Well, I tell you what, let me get my algebra book
Okay.
and see if I can see what a typical chapter on radicals begins with. I do a lot of tutoring on radicals, but because the person usually brings me the problems. Radicals. It's chapter 7 in my book, which seems awfully late. Are you guys that far into your...
No, but we skip around, so there's no, like, guaranteeing that we're gonna
Okay.
go in chronological order.
Now let's go to lots of good problems here. Hold on 1 second. Is that equal to?
Okay, so
Cube root
it's
of 8.
easier if you take the square root first, right? Because
No,
it gets
no.
smaller.
No, this is
No, because it doesn't have a square root. It's
right.
different. Okay,
This is
8 is 2.
This is cube
2.
root of 8 equals 2.
Yeah, duh. Okay,
What
sorry.
does this equal?
Negative 2?
Uh-huh. What does this? Can't do that. Hold on. So if I'm solving the equation and I get this, take the cube root of both sides, so you get negative 2. If I have this, what's x equal to?
4?
Plus or minus 4.
Plus or minus, yeah, because...
And notice the difference. In other words, when x cubed is equal to minus 8, x is equal to minus 2 only, not plus or minus 2. Minus 2 only. In other words, odd roots will give you one answer only, either positive or negative. Even roots always give you a plus or minus.
Okay.
How about this one?
I have a question, but...
Well, go ahead. Yeah, if you have a question, by all means.
No, I don't remember what it was. Like, I had it, and then... I'll tell you.
What does this mean?
Oh, God. Isn't it, like, a weird fraction thingy with x? Or something?
Most important thing to remember about negative exponents is they have nothing to do with negative numbers. Is all a negative exponent means is reciprocal.
Okay.
Okay? So if I have 5 to the minus 2, what does that equal to?
So, okay. Reciprocal, so you have 1 over 1 over 5?
1 over 5 squared. In other
Oh.
words, the only thing we need to do with that is put 1 over the number to the positive exponent. So that's 1 over 25.
Okay. I remember one day, there was some problem where you ended up with something really funky like 1 over x, or like 1 over 2 over x or something like that, and you multiplied it. I don't remember. Never mind. I'm just going to confuse myself. I'm trying to think about it.
Well, let's take this problem. Is that equal to?
X, 9x, or x to the power of 9? X to the power of 20.
No, 9 is
No, I
correct.
was right the first time. Okay.
In other words, when we're multiplying, we add the exponents. When we're dividing, we subtract. As long as it's same base. In other words, as long as it's x and not a different variable y, we can do that. I can say 3 to the 4th divided by 3 squared equals 3 squared, just by subtracting the two exponents. I cannot say anything about 4 to the 3rd divided by 2 to the 7th. This is not the same base, it's not the same exponent. So if it's not the same base and same exponent, you can't do much with it. But if it's either, you can. The last one that's key is x to the a power raised to the b power. What is that equal to?
X to the power of AB.
In other words, in this case, we are exponentiating. Translates the multiplication. Multiplication's one level less than exponentiating. Just like if we're multiplying, we're going to add, and addition is one level less than multiplication. So rules for exponents, just remember that when you have same base, you do one level less with their exponents. The other case is where you have a different base but same exponent. In other words, if I have 2 to the x times 3 to the x, I can do something with that. That's 6 to the x. In other words, a to the x times b to the x is equal to ab to the x.
Okay.
Same with division. In other words, 9 to the x divided by 4 to the x equals 9/4 to the x. So those 5 rules for exponents cover just about doing anything you want with exponents.
Okay.
Let me come up with some good problems. Okay, rewrite this using exponential notation.
Okay. So 14 first, and then to the 1/4. Oh, cool.
Okay. Rewrite this using exponential Hold on.
So, well, you'd have 5 to the 1/7, right?
Right.
And then you would multiply that by 2.
Huh?
So you get 5 to the 2/7.
Right. In other words, this goes in the denominator, this goes in the numerator.
Okay.
Hold on. Okay, this says evaluate the expression without using a calculator.
Oh, that kind of problem.
No, these will be easy. They don't want you to use a calculator, then it means they're going to be whole numbers or whole fractions.
The 16 goes into 64, right? So, divided by 16. So that's the square root of 16 and the square root of 4. It is 2 and 4, 8. No, it's not. That's cubed. Does it work for cubed?
So that answer is 4. In other words, 4 times 4 times 4 is equal to 64. That's what cubed root means, is what number multiplied by itself 3 times is going to equal this.
So for the square roots, you know how there was that list of square numbers?
Uh-huh.
Is there like a list of cube numbers that you can use for
Sure.
cube code?
Yes, and I was going to suggest you memorizing them at least up until 5. Okay, so we have 1. 8 is 2 cubed. 27 is 3 cubed. 64 is 4 cubed, and 125 is 5 cubed. So if I said the cube root of 500, that's divisible by 125. So that's equal to the cube root of 125 times the cube root of 4. Well, the cube root of 125 is 5. So that's 5 cube roots of 4. If I want to reduce
Okay.
that.
So it's the same rules, you just have to use a
Same
different
rules,
list of
yeah.
numbers?
You kind of need to be familiar with these perfect cubes, but I don't know that you're going to get a whole lot of questions like that. You might actually with an honors algebra. Okay, I'll just go through a few more of these from the book.
Okay. Oh wow, okay. Would it be negative 10?
Yes.
Because you can carry over the negative from cubes.
Uh-huh. Now, what about this one?
Oh, okay.
Now know that when they ask you questions like this, the answer is going to be a whole number. It's not going to be irrational. So the whole number is either going to be 2 or 3, right?
Yeah.
Not going to be 4. We know that 4 cubed is 64, so the 6th root of 64 is certainly not going to be 4. It's not 3. How about 2?
No.
Actually, 2 times 2 times 2 times 2 times 2 times 2 times 2 is 64. 2 to the 6th power is 64. So what is my answer?
Negative 2?
This is completely independent from this.
So like it's kind of like when you distribute and
Yes.
it's
Yes.
like that. Okay.
But if I said the 6th root of negative 64, can't do that. That's like taking the square root of a negative number. You can take odd roots of negative numbers, but you can't take even roots of negative number. So this would not be minus 2. It would be 2i.
Ooh, the infamous
Because,
I.
yeah, because that's actually equal to the square root of minus 1 times the square root of 64. I'm sorry, the 6th root. I take that back. That's not 2i. I forgot it was 6th root. The 6th root of minus 1 is not I. The square root of minus 1 is I.
Okay. What does the I mean?
I merely means this. Square root of negative 1. It's called an imaginary number because it doesn't exist. In other words, there are no two numbers multiplied together that equal to minus 1. So mathematicians have made this up because it's useful in doing higher math. You'll get to it if you haven't gotten to I yet.
Okay.
Surprised you haven't gotten to it yet.
I think that might be this chapter, I don't know.
Okay, how about this one? So what's the first thing I do when I see a negative exponent?
It means that you put it in the little fractiony thing.
Reciprocal.
Yes, sorry.
So this is the same thing as this. And then what is 4 to the 1/2?
4 to the, that's 4 square root.
What's the square root of 4?
2, so 1/2.
Right.
Tricky. So cube root 1 is what that's saying?
Cube root of 1 is 1, because 1 times 1 times 1 is equal to 1. In other words, 1 to any exponent is equal to 1. No matter what x is, no matter whether it's positive a billion, a negative a billion, negative a fraction, positive a fraction, 1 to any exponent is 1. Do the denominator first. In other words, the 5th root of 32.
Okay. So, could you just put that,
Yeah, the way I would do this is I would take the 5th root of 32, which is 2, and raise it to the 4th power. Like that.
Okay. Wait. So, you have to, yeah, I guess you actually have to solve it out, don't you? Never mind. No question.
Okay, let's see. Alright, let's do some equations involving exponents and radicals. Well, actually, this chapter I'm on is not so much square roots as it is just radicals and fractional exponents.
I think in the book we used today, it's, I want to say it's chapters 6 and 7 because I was looking today, but I don't know for certain. 6 and 7 and maybe some of 4.
My problem is I don't have your book, so
Yeah,
I don't know what 6 and 7 is. What I'm giving you problems out of is chapter 7 in my Algebra 2 book, so it's probably relatively close. But what's the square root of x squared?
X.
Okay. What is the square root of x to the 6th?
X to the 3rd. X.
Yeah.
Wait.
No,
Yeah.
that's correct, because notice that there's the invisible 2 there. So this is the same as x to the 6th over 2, which is the same as x to the 3rd.
So when you're dealing with like fractions as an exponent, you can still simplify them?
Yes, even if there are variables. Yes. For example, what's that equal to?
That would be, so y is equal to 2 over 5?
5 over 2.
5 over 2, sorry.
Okay.
And
Then that can be simplified because we always want to express any whole numbers of y that we can. So that's the same as what? That's the same as y squared times y to the 1/2, right? Because that's, if you add those exponents, you get 5/2. So the answer really is y squared square root of y. In other words, I'm going to take 4 of these y outside the square root sign, leaving 1 behind. And the 4 that I take outside the radical sign, I have to cut that exponent in half because I'm going to take the square root of it. So that's where I get my y squared. In other words, it's really y to the 5th is the same as square root of y to the 4th times square root of y. And this is y squared.
Okay. Okay, so it's like advanced math rules. Like the same rules but different. Okay, I got this. Maybe. You can't have, like, what do you call the number outside this radical?
The root.
The root? So you can't have a root of 1 or 0, right?
Correct.
Okay.
You wouldn't use the radical sign. The radical sign is only used when you have roots of 2 or greater. In other words, if I wanted the 5th root of 32, that's what I would say. That's also equal to 32 to the 1/5. It's also equal to the number 2.
Okay.
How about this problem? Again, I realize this might be a little advanced, but probably not. I'm guessing you will be covering problems like this in the next day or two.
So you, okay. So you can have 5 to the 1/5.
Okay. Okay, let's go ahead and do it like that. I like doing that and converting everything to fractional exponents and then going from there.
And then A, just A.
Uh-huh.
And then B to the 9/5. And then C to 13/5.
Okay. That's not in simplified form because these can be reduced.
Okay, so then you take out...
Can't change 5 to the 1/5. That's as reduced as it is. But let's take as many whole B's out of there as we can get out.
So 1B you could take
Yeah.
out?
I can take out 1B, and that leaves another B to the 4/5. Let's do the same thing with C.
2C, so C squared, and then, like, 8 3/5.
Okay. Now, since they gave it to me in radical format, usually they want the answer in radical format. In other words, I don't want to leave the answer with exponents. I want to put it back into the format that they gave me. So I would use the 5th root symbol. My 5 would go under there. My B to the 4th would go under there, and a B outside like that. My C to the 3rd would go under there, and I would have this C squared outside. So that would be what that simplified to.
Okay. So you just put it back. Or you take out all your whole numbers.
There's nothing more correct about this answer than this answer. They're both equally correct. And you might not even lose points on a test if you gave that as the final answer. But usually what I've found is that if they start in radical format, they want it ending in radical format. If they start in exponential format like this, then you could leave this as a final answer, exponential format. That's kind of what I believe the rules are. Certainly the examples I'm looking at in my book, that's what they do. If you start with a radical question, you end up with your answer in radical also. Oh, I left out the A, didn't I?
Yeah, but...
Sorry. And don't misinterpret this. That is not B to the 5th. That is B. That 5 just goes with the radical sign.
Would it be incorrect if to, like, differentiate between the B and the radical sign if you put, like, a multiplication dot
Yeah, not a multiplication dot, maybe a parentheses though.
Parentheses? Okay.
Yeah, I like that better. The dots tend to get lost when you're working with a lot of variables because x, y, z automatically means x times y times z. We don't tend to put dots in front of them when we get to variables. So don't rely on somebody seeing a dot if you put it in on a question like this. Whereas parentheses they'll always see, and parentheses mean the same thing as dots do.
Okay.
Let me give you one more here. Wow, I got to figure this one out. Hold on. This one's kind of clever. This is really exotic, but
Alright. So start by distributing the roots. You'd have x to the 1/3.
okay.
Can you do that? And then over y to the, oh god, 7/3.
Uh-huh.
And then you have to simplify that, so you take out y squared.
Okay, you're doing good.
X to the 1/3 over y to the 1/3. 2y squared to the y/3. 1/3. And
Okay.
then can you simplify out these? You can't, right?
Well, they do an interesting thing in the book here. This is not the way they did it. I actually prefer this way, the way you did it. And I think this is a okay final answer. Let me show you what they did, just because it was a little clever. They multiplied this fraction by y squared over y squared. And what that gave them was the cube root of xy squared over y to the 9th. So now we have the cube root of xy squared over y cubed. So this perhaps is a better answer, and I just realized why. Why this top answer is not the best answer.
Okay.
It's irrational. It's got an irrational denominator. When you take the cube root of y, that's irrational, usually. I mean, unless y is like 8 or 64. But if y is any typical number, you're going to have an irrational denominator. So they basically rationalized so that the denominator would be a whole number. Y cubed is always a whole number. These two answers are the same. Don't misunderstand me. No matter what x and y are, they're the same answer. But
how did they get the y squared to the numerator?
just by, you can multiply any fraction by the number 1. So in that step right there, they just multiplied top and bottom by y squared.
But did they do, like, I'm trying to understand what they did here. Did they do y squared times y and 1/3 over y squared times y and 1/3? Is that how they...
If they went directly from this step to this step. In other words, the numerator becomes xy squared, and the denominator becomes y to the 9th. But now when you take the cube root of the denominator, you get a perfect y to the 3rd. You still have the cube root of the numerator, which is the cube root of xy squared, but that's okay. There's actually an example in my book, and this is the way they do it, and this is the answer they give for this problem. Okay, let's see. Oh well, let's see, it's 4:30. I guess we better end our session so I can work with your brother.
Okay.
Okay?
Thank you.
All right. I will talk to you on Saturday.
Yeah, see you Sunday.
Or Sunday.
All right.
Excuse me, Sunday.
All
All right,
right.
sir.
Have
All
a
right,
good
sir.
evening.
You too. Bye-bye.
Bye.